Welcome back, everyone. Today we're diving into an explainer that literally shrinks us down to the atomic level. We're going to explore the fascinating solid state of matter. Basically, we're uncovering the hidden microscopic architecture of literally everything you can touch, hold, and interact with on a daily basis.
Here's our blueprint for today. First up, classifying the solid world, followed by the ultimate building blocks, packing efficiency and density, perfectly imperfect crystal defects, and we'll wrap it all up with doping and magnetic superpowers.
Okay, let's jump right into Section 1, classifying the solid world, order versus chaos.
It all really comes down to a structural battle of order versus chaos. Notice the stark contrast here. On the one hand, we have crystalline solids. These are your strict rule followers. They have exact, regular, repeating patterns and incredibly sharp melting points. Think of a flawless, rigid diamond. But then on the other hand, we have amorphous solids, like tar or glass. These are completely random. They lack any true internal structure. And honestly, structurally speaking, they behave a lot more like messy, supercooled liquids that just kind of froze in place.
Now, those highly organized crystalline solids, we can actually break them down further into 4 distinct structural families based on their internal bonding superpowers. First, you have ionic solids, like your everyday table salt, held together by really strong electrostatic forces. Then there are covalent solids, which form massive, rigid networks. Think quartz or diamond. Molecular solids, like solid ice, rely on much weaker forces. And finally, metallic solids, like silver and copper. These are basically just an array of positive ions floating in a literal sea of mobile, free-flowing electrons.
Moving right along to Section 2, the ultimate building blocks, mapping the micro.
Let me introduce you to the unit cell. You can think of this as the ultimate microscopic Lego brick. Because crystals are perfectly periodic, if you know the exact 3D shape and geometry of just one of these tiny unit cells, well, you automatically know the shape of the entire massive crystal lattice. It's like a giant puzzle where every single piece is perfectly identical. But here's the crucial point, and it shows just how incredibly creative nature is. Sometimes a single substance can arrange its unit cells into entirely different geometric shapes. This structural shape-shifting property is known as polymorphism. It's the exact reason why pure carbon can be both the slippery graphite in your pencil and a super hard diamond on a ring. Same exact atoms, completely different architecture.
Up next is Section 3, packing efficiency and density, the geometry of space.
Imagine trying to pack a bunch of perfectly round basketballs into a square box. How tightly can we pack these atomic spheres together without leaving too much empty, wasted space? Well, let's look at the simple cubic system. Here, atoms only sit at the corners of the cubic unit cell, meaning there's effectively only one atom per cell. And honestly, this is shockingly inefficient. We're leaving nearly half the box, 47.6% to be exact, completely hollow and empty. But if we build on this with the body-centered cubic or BC structure, things improve quite a bit. By placing atoms at the corners and then dropping one right in the center of the body, we now pack in 2 atoms per unit cell. Our packing efficiency jumps up to 68%, which drops that empty free space down to a much better 32%.
And the absolute winner in our geometric packing contest? That would be the face-centered cubic structure. By placing atoms at the corners and right in the center of every single face of the cube, we effectively cram 4 whole atoms into the unit cell. This achieves a massive 74% packing efficiency, leaving only 26% empty space. It is literally nature's ultimate space-saving hack.
All right, let's look at Section 4, perfectly imperfect crystal defects, breaking the matrix.
We've spent this whole explainer building the perfect crystal with maximum efficiency, right? But here is the most fascinating part of solid-state chemistry. What happens when that perfect crystal breaks its own rules? Look at the contrast between our 2 main point defects. The Schottky defect is kind of like a buddy system gone completely wrong. An equal number of positive and negative ions simply vanish, leaving empty vacancies. Because physical matter is literally missing, the overall density of the crystal drops. The Frankel defect, on the other hand, is like a displaced wanderer. An ion leaves its normal spot but gets safely stuck in the gap, the interstitial space, between other atoms. Since nothing actually left the crystal structure, the overall density remains exactly the same.
But this defect right here, the F center, this is my absolute favorite. Sometimes a negative ion leaves a vacancy and a single lonely electron gets trapped in that empty space. This trapped electron acts like a magical color bomb for the crystal. By absorbing specific wavelengths of light, it imparts these brilliant, vibrant colors to crystals that would otherwise be completely transparent or just dull white.
Let's actually see this in action. If you follow these exact steps, say heating a normal white sodium chloride table salt crystal in an atmosphere of sodium vapor, the chloride ions rush to the surface. Then the sodium releases an electron, and that electron falls right into the vacant trap. Just like that, your plain table salt crystal starts glowing with a vibrant, brilliant yellow color. It's basically an amazing microscopic magic trick.
And that brings us to our fifth and final section, doping and magnetic superpowers, designing the future.
Now that we know defects exist, let's explore how intentionally adding impurities, a process known as doping, creates the very electronics we rely on every single day. Let's look at our first doping recipe. You start with pure silicon, which has 4 valence electrons. But if we sneak in a tiny, minute amount of a group 15 element, like phosphorus, which has 5 valence electrons, well, we have 1 left over. That extra electron excitedly enters the conduction band, forcefully creating a highly conductive, negatively charged N-type semiconductor. Conversely, look what happens when we drop in a group 13 element like boron. Boron only has 3 valence electrons. This leaves us 1 short, creating an electron hole. This positive void conducts electricity just as effectively by allowing electrons to jump into it, giving birth to a p-type semiconductor. And stacking these N-type and p-type materials together? That's exactly how computer chips, solar cells, and LED screens are manufactured.
It gets even cooler, because these microscopic electron structures don't just control electricity, they dictate a material's magnetic superpowers too. We can cleanly split materials into 2 categories based on their electrons. Diamagnetic materials have 0 unpaired electrons and are actually weakly repelled by magnetic fields. Paramagnetic materials, though, contain unpaired electrons that act like tiny magnets themselves, making the material weakly attracted to external magnetic fields.
It's an absolutely incredible thought. We started out mapping perfect geometric cubes, but the crucial takeaway is that the intentional breaking of those tiny, invisible boxes is what actually powers the device you're watching this explainer on right now. The deliberate flaws are what make the solid state so incredibly powerful. So as you look around your room today, I want to leave you with this question. What other hidden structures and intentional, brilliant flaws are silently powering the world around you right now?